Your classifier can be accurate and still dangerously overconfident. You'll use temperature scaling in PyTorch and scikit-learn to turn sharp logits into usable probabilities. This is the setup you'll be able to run after this, which learns a single temperature from validation scores and makes risk-aware decisions on new scores. I'm Professor Pi, teaching AI foundations with simple Python. Calibration matters when decisions use probabilities. A model can get many labels right and still lie about how sure it is. That breaks downstream choices like sending alerts, routing cases, or estimating risk. Temperature scaling is a tiny, cheap fix you apply after training. It learns one number on a validation set and rescales logits so the probabilities better match reality. The idea is simple. Models produce scores called logits. Dividing those scores by a temperature makes the softmax output softer or sharper. A temperature above 1 spreads mass more evenly and reduces overconfidence. It does not change the predicted class labels much, but it changes the probabilities you trust. We will build a small synthetic classifier, learn one temperature on validation logits, and then apply it to a test set. You will see numeric metrics that show improved probability estimates and a concrete thresholding example that translates probability gains into fewer false alerts. Now we'll simulate an overconfident classifier and inspect its confidence and accuracy. This snippet simulates an overconfident multi-class classifier in PyTorch and contrasts confidence with accuracy. We seed the generator for reproducibility, then create base scores for 3 classes using random normals. The variable y holds ground truth labels sampled from f.softmax base, ensuring plausible class frequencies. We form overconfident model logits by scaling base with 3.0 and adding small noise, which exaggerates score gaps. The tensor P contains predicted probabilities via f.softmax logits val. We compute the mean maximum probability as a proxy for model confidence and compare it to classification accuracy from the top 1 predictions. A large gap in the printed numbers signals miscalibration worth fixing. Next, we learn a single temperature on the validation set using gradient-based fitting. This code fits a temperature parameter in PyTorch to calibrate validation logits by minimizing cross-entropy. The scalar t is a learnable parameter mapped to a positive temperature t using f.softplus, ensuring stability. We use torch optim atom to update t over 200 steps, each time computing the loss as f.cross-entropy on logits val divided by t. Lowering the effective logit scale, higher t, typically softens probabilities and reduces overconfidence. Decreasing t would make them sharper. After optimization, we read back the final t and compute the validation negative log likelihood for reporting. A moderate t greater than 1 with a reduced NLL indicates improved calibration on the holdout. Then, we measure the numeric effect on log loss before and after calibration. This example uses scikit-learn's log loss to quantify calibration improvement before and after temperature scaling. We convert the PyTorch probability tensors to NumPy using detach and evaluate pre as f.softmax logits val and post as f.softmax logits val divided by t. The array y and p holds integer class labels compatible with scikit-learn. The function log loss computes the multi-class negative log likelihood for each set of probabilities, which is sensitive to probability calibration quality. We subtract post from pre to get a drop value. A positive number means calibration helped. The printed log loss decrease shows that the learned temperature improved the probabilistic fit, not just the hard accuracy. Next, We check generalization with a fresh test set and a Brier score for one class. This snippet measures generalization by evaluating calibration on a held-out test set and computing scikit-learn's Brier score loss for a chosen class. We synthesize new test logits similar to validation and reuse the learn temperature T. The arrays pre and post hold uncalibrated and calibrated probabilities, respectively. We focus on class 1 by forming a binary target YB and extracting the corresponding predicted probabilities pre:1. The function Brier score loss measures the mean squared error of predicted probabilities, lower being better. A positive drop indicates improved probability accuracy on unseen data, which supports using the calibrated model in production settings. Now we translate better probabilities into safer actions with a threshold and precision. This code applies a decision threshold to demonstrate how calibration improves risk-sensitive actions using scikit-learn's precision score. We set THR to 0.8 on the class 1 probability and build Boolean selections pre-cell and post-cell from the test set probabilities defined earlier. The function precision score compares these selections against the binary ground truth YB, reporting the fraction of selected items that are truly positive. Higher precision at the same threshold means fewer false alarms among high confidence alerts. If you raise the threshold, you'll typically get even higher precision with fewer alerts. Lowering it increases coverage, but may dilute precision. The printed precision gain validates better trust in calibrated confidence scores. In a real system, this maps directly to fewer false high confidence alerts. Treat class 1 as the positive condition you care about. The calibrated scores let you pick a threshold that balances missed cases and false alarms in an interpretable way. Recap. What it is: a post-training rescale of logits that makes probabilities more truthful. When to use it: when your model is accurate, but probabilities are too confident or too timid. One caveat: it only rescales logits globally and may not fix per class or systematic biases. Next step: try learning per class temperatures to see whether different labels need different amounts of softening. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.